Now that we've talked about ionic and molecular compounds, we can further delve into types of bonding. So in this unit, we review how single atoms combine to form compounds or molecules. So the bonds that hold together compounds or molecules, those are called intramolecular bonds. And what this describes is the bonds that hold together atoms within the molecule. So very important that you're able to distinguish between intramolecular bonds and intermolecular bonds. So for example, for intra, like that word specifically means within. Okay, so if you think about something like IV, so intravenous, okay, that is providing fluids within just one person. It does not transfer fluids between two different people. Okay, so that's one way that you can help yourself. Remember that intra means within the same molecule. So this is an important definition. Make sure you highlight this. Now, there's two types of intramolecular bonds. The first type is going to be covalent bonds, which are specifically for molecular compounds, which we're going to get into. And then the other type of intramolecular bond would be ionic bonds, which are for ionic compounds. So the type of bond depends on the types of elements that make up the compound and their electronegativities, okay, which is a definition we're going to get into a little bit lower down in this page. So we then look at how numerous atoms, ions, or molecules bond together to form relatively large lumps of matter. These types of bonds, which are between different molecules or different compounds, those are going to be called intermolecular bonds. Okay. So super important that you know that inter means that it's between two different compounds, two different molecules, so on and so forth. And I'm going to adjust this to separate molecules or compounds. That's more accurate. Okay. So some examples for intermolecular bonds, which we will eventually get into, would be London forces, dipole-dipole, as well as hydrogen bonding. Okay. So going back to intramolecular bonds. So again, this is binding atoms within a compound. And as stated, there's two different types. There's ionic and covalent bonds. So ionic, that belongs to ionic compounds. whereas covalent bonds, those are going to belong to molecular compounds. So the type of bond depends on the types of elements that make up the compound and their electronegativities. So let's move on to what is electronegativity. So the electronegativity of an element is the ability of the element to attract electrons within a bond. So let's add that in. And that is an important definition, so make sure you highlight that. The larger the electronegativity value, the greater the strength that the element has to obtain the electrons. So typically for electronegativity, the Pauling scale is used, which typically ranges from 0 to 4. So, for example, if we had an atom that had an electronegativity of 4 versus an atom with an electronegativity of 1, the atom that has the electronegativity of 4 is going to be the quote-unquote stronger atom, and therefore has a better ability to attract the electrons within the bond towards itself. So let's write out what I just said. And you could kind of think of electronegativity as how strong an atom is at pulling electrons towards itself within a bond. So you can kind of think of this as, if I draw a little stick figure here, okay, and we have two people, one stronger than the other. So this stick figure here, we're going to pretend that this is the weaker of the two people. Okay, whereas the one on the left, that's the stronger of the two people. So if they're playing a tug of war, and this is like a little knot in the middle of the rope, okay? So obviously the person who's stronger is going to be able to pull the rope more towards them, or pull the knot towards themselves, okay? And this is a pretty good analogy for when you're thinking about electronegativity. The more electronegative an element is, the quote-unquote stronger they are. So the more they're able to pull the electrons within the bond between two atoms towards itself, and itself being the more electronegative of the two atoms. And just to cap off this analogy here, the knot in the rope represents the electrons in the bond. Now, just how far these electrons in the bond get attracted to the more electronegative atom or more electronegative element is going to depend on the types of elements involved in the bond. So, for example, for ionic compounds, which are made up of ionic bonds, the electrons get completely transferred from the metal to the non-metallic element. Okay. Whereas for molecular compounds, which are made up of covalent bonds, the electrons are still going to be shared between the two atoms of non-metallic elements. However, the electrons within that bond are going to be kind of skewed more so towards the side that has the higher electronegative element. So we've got two examples here, and it's asking us to put these atoms in order of electronegativity. So if we take a look at our periodic table here, let's find the first element, which was Ti, or titanium. So titanium is right here. Now, looking at our periodic table, this is the atomic number, this is our electronegativity value, and these are the two charges. So atomic number, electronegativity, and then the charges. Okay, so we see that titanium has an electronegativity of 1.5, so let's write that out. Next one is going to be manganese. Let's check that one out. So manganese is right here. It has an electronegativity of 1.6. Next one is selenium, which is right here. So it has an electronegativity of 2.6. Potassium, let's see, potassium's a metal, so it's all the way over here. It has an electronegativity of 0.8. Bromine, let's see, that has an electronegativity of 3. And then tin, that's going to have an electronegativity of 2. All right. Just going back to the periodic table, if you ever wondered why some of the elemental symbols don't necessarily match up with the English name for that element, it's just because some of these elemental symbols are based off of the Latin names for these substances. So, for example, the Latin name for tin is stannum, so that's where we get the symbol SN. All right, so now that we have all our numbers, let's organize these electronegativities from smallest to largest. Oop. Okay, so our element with the smallest electronegativity, that would be potassium. So let's cross that one out. And then the next largest electronegativity, that would be titanium. and then we have manganese. And then our next one is going to be tin. And then our next one would be selenium. And then our last one would be bromine. And I'm just going to adjust this S so it's a bit more clear that that's a capital. And there we go. Okay. So as you can see, the non-metallic elements have a higher electronegativity compared to the metallic elements, just in general. Okay. With the next example, same sort of concept. So let's figure out what the electronegativities of all of these elements are, and then we can arrange them from smallest electronegativity to largest. Okay, so with fluorine, that one's pretty easy because that's the element with the highest electronegativity. It's right at 4. Bromine, we found previously, that was at 3. Iodine, that's at 2.7. Okay. Astatine, that's at 2.2. And then chlorine, let's see. Chlorine is at 3.2. So let's order these from smallest electronegativity to largest. So the first one, that's going to be astatine. Okay, our next biggest one will be iodine. Then bromine, then chlorine, and then fluorine. So since all of these elements, since all of them are halogens, okay, we can see that as we move up a group, so if this is the halogens are group 17. As we move up a group, the electronegativity is going to increase. So the trend here of the periodic table is typically as you move to the right in a period, so a row, or if you move up within a group, the electronegativity is going to increase. So all atoms prefer to have their outermost energy levels filled to the maximum capacity. Why? It's because it makes them more stable. Okay, and there's 2 ways for atoms to achieve stability. One way is to transfer electrons. So this symbol right here just means electrons, which that happens specifically for an ionic bond, which happens in ionic compounds. And the other way for atoms to achieve stability is to share electrons, which that happens in covalent bonds, which are in molecular compounds. So as a quick refresher, an ionic compound is created when a metal and a nonmetal bind together. A molecular compound is formed when 2 or more nonmetals are bound together. So covalent bonds, as we've said, this is for molecular compounds. It occurs between two or more nonmetals. And the electrons are shared between them. Okay. Now, as I've discussed previously, sometimes the electrons are shared equally between two nonmetals. However, other times they can be shared unequally. And this is what creates polar covalent bonds versus nonpolar covalent bonds. So polar is when the electrons are shared unequally. And this happens when one element is more electronegative than the other. One element, or I probably should be saying one atom, is more electronegative than the other. Whereas nonpolar, the electrons are shared equally. And this happens when both atoms that are on either side of the bond have the same electronegativity. Okay. So again, for our two types, just like delving into a bit more detail about this equal sharing that comes from the two atoms having the same electronegativity. Unequal is when there are different electronegativities. So since this is information that I'm repeating, and this can apply throughout this whole video series, the more information is, or a piece of information is repeated, the more important it is. So for example, polar versus nonpolar covalent bonds, you will need to be able to distinguish between the two of them. And just looking ahead, you'll have to be able to identify polar compounds versus nonpolar compounds. So that's why it's important. Okay, so some examples of nonpolar covalent bonding would be something like if we had a diatomic element, such as fluorine. So remember, the memory device or the mnemonic device for all of your diatomic elements, that's Hofbrinkel. Okay, so both fluorine atoms have an electronegativity of 4, so both of them are pulling on the electrons within this bond with equal strength in opposite directions. Okay, so these arrows, they're called dipole arrows. Since they're in equal and opposite directions, they essentially cancel out, and that's what tells us that this bond right here is nonpolar, or nonpolar covalent. Okay, an example of unequal sharing of electrons. That's going to happen in a polar covalent bond. Something like that would be a bond between hydrogen and fluorine. So we know that fluorine has an electronegativity of 4. Let's take a look at what hydrogen is. So hydrogen has an electronegativity of 2.2. So as we can see, fluorine is the more electronegative, or the stronger of the two. So it's going to, like, the electrons are still shared between hydrogen and fluorine. They're just more skewed towards the side that the fluorine atom is on. And what that creates is a side of this molecule that has a slightly positive charge. That's why there's kind of like a positive symbol on this side of this dipole arrow. And a side of this compound that has a slightly negative charge. Okay. So unlike ionic compounds, molecular compounds, they don't form crystal lattices. Ionic compounds can form crystal lattices. But for molecular compounds, they just exist by themselves. Okay. So, for example, glucose that exists as a solid. But it's not going to form a crystal lattice, which is something only ionic compounds can do. And since glucose is a molecular compound, that's why it doesn't form a crystal lattice, which is a subject we will get into right after this. With water, once again, that does not form a crystal lattice, and this is in the liquid state, which I'm going to switch this to just be S for solid. L is for liquid for the water. So since they are not crystal lattices, molecular compounds can be in the solid state, liquid, or gas at room temperature, and typically they have low melting points, whereas ionic compounds, they're going to have high melting points. So if crystals do form, so note that it's saying crystals and not crystal lattices, the crystals are going to be brittle and very colorful. Now, for ionic bonds, those are for ionic compounds, okay, which is formed from when you have a metal and a non-metal. And in ionic bonds, there's going to be a complete transfer of electrons, which is what makes the ions. So when the metal atom loses its electron and gives it to the non-metal atom, that is what creates ions. Okay, so for example here, we have lithium and fluorine. So lithium, that is our metal atom because it's to the left of the staircase on the periodic table. And as we can see here, it's donating or giving its outer valence electron to fluorine. So metals always are going to be giving their electrons to nonmetals. Okay? And it's in this transfer of electrons that ions are going to form. So once the lithium atom loses its valence electron, it becomes a lithium ion. And then once the fluorine atom gains an electron, it's going to become a fluoride ion. And so together, that creates an ionic compound called lithium fluoride. Okay. Now the question is, why is an ionic bond formed between the lithium and fluoride ion. What causes the attraction? Well, it's all about the attraction between the positive charge of the lithium ion and the negative charge of the fluoride ion. And so with this, opposite charges are going to attract, and we call this in chemistry electrostatic attraction, which is just opposite charges are going to attract, and the ionic bond formed between this electrostatic attraction is going to be incredibly strong, and that's why ionic compounds typically have a higher melting point than molecular compounds. It's just because ionic compounds form stronger bonds than molecular compounds. Okay, so opposite charges attract, which is called electrostatic attraction. Okay, so the positive charge is attracted to the negative charge or vice versa. So as kind of briefly mentioned, ionic compounds, those form crystal lattices. And what a crystal lattice is a regular repeating arrangement of atoms. Okay, so it's repeated over and over and over again. Okay, so for example, this right here is a crystal lattice of sodium chloride. Okay. And then down here, this is another crystal lattice, but we don't have enough information to see which ions are forming the crystal lattice, but we do know like red is one ion, it may be the cation or it may be the anion, and then purple is the other ion. Okay, so looking back at this diagram here, since it's more clearly labeled, the small red circles, those are going to be your sodium ions, whereas the big green ones are going to be the chloride ions. Now, sodium is smaller or represented smaller than the chloride ion in this diagram, and it's simply because the sodium ion has less protons compared to the chloride ion, which is going to be bigger because it has more protons, or just in general more substance making it up. Okay, and by substance I mean subatomic particles. Okay, so since ionic compounds all form crystal lattices, they're all going to be solid at room temperature. And most are either going to be gray or white in color. Okay, that's not to say that ionic compounds never have any color to them, but the vast majority of them are either gray or white. Okay, so as said, ionic bonds are incredibly strong. And because of these incredibly strong ionic bonds, that are formed because of these electrostatic attractions, that's what causes ionic compounds to have high melting points. All right, so since we've talked about ionic and molecular compounds here, and it is very important for students to know the difference between the two, let's just create a compare and contrast table. Okay, so starting off with ionic compounds. Okay, first off, ionic compounds are created when you have a metal and a nonmetal. Okay, and one of the exceptions for ionic compounds, or for things that can create an ionic compound, would be ammonium, which is NH4+. And since it's a cation or a positive ion, it's going to act like a metal. Now, when we're naming ionic compounds, you do not use prefixes. That's specifically for molecular compounds. Okay, and when we have ionic compounds that contain multivalent metals, so that's a metal that has more than one possible charge, we have to use Roman numerals to specify the charge, not how many atoms of that particular metal there is. For ionic compound names, they're going to end in IDE unless your compound contains a polyatomic ion. So with polyatomic ions, remember you don't change the ending of their name necessarily to IDE. You write the name of the polyatomic ion exactly how it shows up in your periodic table. And if we take a quick look at it, you can find all of your polyatomic ions right here on your periodic table. Okay. And then I'm going to have to squeeze the last 2 points in here. Okay, so ionic compounds, they're formed when electrons are transferred. And when you're creating a chemical formula for an ionic compound, you always need to balance the charges. Now for molecular compounds, so if ionic compounds are created from a metal and a nonmetal, molecular compounds, those are created from two nonmetals. And molecular compounds, when you're naming them, they use prefixes. Okay. So our prefixes are mono, meaning you only have one atom of a certain element, di meaning 2, tri meaning 3, tetra meaning 4, penta meaning 5, so on and so forth. Okay. Now, there are exceptions to the prefix system. Okay, so one of the few times you don't use prefixes is when you only have one of the first element in a molecular compound. And by one, I mean one atom. So for example, if we have PCl3, that would be phosphorus trichloride. So we're not going to say monophosphorus trichloride because phosphorus is the first element, and when there's only one of them, you just say the element name. Okay, you don't need a prefix for it. Okay. And the other exception would be hydrogen-containing molecular compounds. Those do not use the prefix system. Okay. So something like, for example, H2S, we would call that hydrogen sulfide. So in covalent bonds, which are in molecular compounds, electrons are shared. Okay, and you can have polar covalent bonds, which is when you have different electronegativities of your atoms that are on either side of the bond, or you could have nonpolar covalent, which is when either atom involved in the bond is going to have the same electronegativity. Last but not least, we have metallic bonds. So those form when colliding atoms with low electronegativity share electrons, but no chemical reaction occurs. So it's caused by a random attraction of the positive nucleus to the free-flowing valence electrons of nearby atoms. And the electrons are shared sort of in a sea of electrons. So with the different types of bonds, the most important ones are ionic bonds and covalent bonds. And you just need to be aware that metallic bonds do form, so that's between two metallic elements. And essentially what that's doing is electrons are just shared amongst these metallic elements, and I guess I should say metallic atoms, seeing as it could be atoms of the same element or different elements. And they're just shared as a sea of electrons. This is probably the more important part here.